In this example, I'm going to do a one-way chi-square goodness of fit test. I'm using some hypothetical data where we've sampled 100 people, 100 students, and asked them where they ate their lunch. So 35 of those people indicated that they got lunch on campus, 21 indicated that they got lunch from home, 14 indicated that they got lunch off campus but not from home, and 30 indicated that they did not get lunch at all. I want to see if these expected frequencies deviate, these observed frequencies deviate from the expected frequencies if we were to assume that 30% would get lunch on campus, 30% would get lunch from home, 30% would get lunch off campus but not from home, and 10% would get no lunch at all. So first we need to calculate, before we can use the chi-square formula to determine if there is a significant deviation between our observed and expected frequencies, we need to compute our expected frequencies. The chi-square formula we'll be using will take the observed minus the expected frequencies. We will square the difference and then divide by the expected frequencies, and then finally we'll take the sum for each cell and add it up. Alright, so to get the expected frequencies, we'll simply multiply the expected proportion for each cell by the total sample size. So for the first cell, the expected proportion is 0.3 and the sample size is 100, so 100 times 0.3 will give us 30. And that will give us the same value for the next three, since those are each expected to have 0.3 is the expected proportion, so the expected frequency is going to be 30. The last one is 10, so the expected frequency 100 times 0.10, or 0.10 is 10. So now we can go ahead and compute the chi-square value for this test. So we have 35 minus 30, so observed minus expected squared, 35 minus 30 square, and divide by the expected value, which is 30. Do the same for the next cell. We'll take 21 minus 30 square it and divide it by 30, and then finally 14 minus 30 divided by 30, square it and divide it by 30, and the last one is 30 minus 10 divided by 10. So we can go ahead and follow order of operations. So we will subtract, square, divide, and then add. So we have, for the first cell, 0.8333. For the second cell, 2.7. For the third cell, 8.533. And then for the last cell, we have 40. So if we add those values together, we get roughly 52.07. Which is a rather large chi-square value. Our degrees of freedom are the number of cells, which I'll call K, the number of cells minus 1. Since there's 4 cells in this design, our degrees of freedom will be 4 minus 1, which gives us 3. So we can look up, I mean this is almost certainly going to be statistically significant, but we can say with 3 degrees of freedom, and let's say alpha 0.05, we would need to get to a chi-square critical value of at least 7.81. We've greatly surpassed that. We could also look up the corresponding p-value to our observed chi-square value. So 52.07 is what we got. And with 3 degrees of freedom, we have 0.0000000002 is basically a very small, incredibly small probability of finding these results if the null hypothesis is true. And here the null hypothesis would be that the expected proportions or frequencies are equal to the observed proportions or frequencies. So we can be pretty confident in rejecting that from these data. It seems that this difference is primarily driven by the number of people who did not eat lunch was much greater than what would be expected by just chance deviations from the expected value of 10. So that's how you compute a goodness of fit, Pearson's goodness of fit chi-square using hand calculations.